This is the second take on diffusion. And this is from that Langevin take. The Langevin, or I'm not French, Langevin dynamics. That's what. So here's the big motivation. Let's say this is us. This is us. And do you know who that is? Not Langevin. You know this person. Hinton. Oh. I Googled Hinton. Give me a cartoon of Hinton. That's what it gives. So here is the problem motivation. I am this person. I say, I have images X, many images X. Can you generate more samples of real images? This is what I'm asking Hinton. Hinton says, do you have P theta X? Right? That's the first thing to ask. If you have P theta X, Hinton, what will Hinton do? Suppose I give P theta X to Hinton. What will Hinton do? Sample from P theta X and give me images. Click game over. I say, no, I don't have P theta X. I'm smart enough that if I had that, I would have known. I wouldn't have asked you. Right? What can I do? Hinton says, can you give me grad X log P theta X? Remember that score, right? Can you give me grad X? Yeah, this is grad X. Grad is gradient. I say, I don't even have that. Right? Then Hinton says, okay, can you give me your images, the images that you have X? Can you add some noise to the images and give me Y? Which is basically the images with some noise in it. I said, no, that is very easy. I have my images, I'll just sprinkle some noise in each of them and I'll give it to you. That's Y. I do that. And I give those Y1 to N to Hinton. Hinton says, wait, I'll do Langevin dynamics on it. Okay? And Hinton figures out how to compute grad log Py. Okay? That's the score. And from that, it can sample. If I have grad log Py and I do Langevin dynamics, then I can get samples from what distribution? If I have grad log Py, and if I do Langevin from Py, I get samples from Py. If I have samples from Py, and if this noise I make it small, then I have samples from Px. You see that? So Hinton will say, hey, add a little bit of noise and give me Y. I will get score of Y. I'll sample. I'll get samples from Py. I'll give you those samples. Those are pretty close to X. So when he says, here are samples from log of Py or from Py, you say, hey, but I wanted samples from P theta X. Why are you giving samples from Py? And Hinton says it's the same. Since you added negligible noise, so Y samples almost same as X samples. You say, that's a magic, right? I wanted samples of X. I've gotten samples from Px, although I actually got samples from Py, but Y is close to X. So I say, yeah, I got samples from X. They should give you the Nobel Prize. What do you think Hinton said? They already did. Right? Okay. Huh? The physics. We should have that caveat always. Okay.
So what is the role of noise here?
What is the role of noise?
Yeah.
We'll talk about that. But the high level answer is when you add noise to X, you get Y. And from that Y, it's easy to calculate the score of Y, which is grad log Py. But it's hard to calculate the score of X. And that's what we'll see. How? Why?
At this point, we're not expected to connect this with the previous one.
This is a different way we'll arrive at the same diffusion thing. But we'll look at it differently.
But at the end, you will see they are the same.
All the same.
But not now.
Not now.
But no. There's no one-to-one analogy here.
So let me introduce you to what is called classic inverse problems. If In classic inverse problems, y is a function of x plus some noise. So in the linear case, y equals cx plus n. Okay. And n is, let's say, Gaussian noise. So here you can think of y being some noisified picture but rotated. Okay. Where did the noise come from? The noise came from this end, right? Where did the rotation come from? From C, right? So this is what you have. Now I ask you, given this image, can you figure out this image? This is an inverse problem. Observe that from this image, there can be many possible x's. I want to find the right x. Classic inverse problem, signal processing people have done this for decades. Beautiful algorithms there. Okay. More applications here. In fact, we are interested in this application. We are working on it right now. A person walks around in her home, and somehow you know the trajectories of that person inside the home. I give you the trajectory and I say, can you estimate the floor plan of this home? Okay, do you see that? Why is that an inverse problem? If I give you the floor plan and I ask you to compute how a person would walk in that floor plan, that's easy. In fact, someone said that's likelihood. Given the floor plan, I can easily figure out which all trajectory fit the floor plan. But if I give you the trajectories, many floor plans might fit that trajectory. That's an inverse problem. Right? When you do magnetic resonance imaging of your brain or of your body, you get a very noisy, very different kind of an image. You don't get a sharp image of a tumor. So the image that you have is some function of the tumor plus the hardware noise of your MRI. From that image, you need to get what that sharp tumor image looks like. Lots of work in this. Okay? So your goal is to basically estimate x hat from y. Okay? So now what do? See, to estimate this, the basic idea is I want to find which x maximizes this conditional distribution. Let's say y are trajectories of a person walking around in a home, and x are all the possible floor plans. Right? Every floor plan has some probability given the trajectory. You agree? If the trajectory and the floor plan intersect, that floor plan must have probability 0. Why? Floor plans are like walls. Right? If the trajectory and the floor plan's walls intersect, that floor plan has 0 probability. Tell me why. People cannot walk through walls, right? So that floor plan is 0. Right? If there is a floor plan which has a huge space which has no trajectory in it, that probability is also probably low. That floor plan's probability. Right? So for every floor plan, you can think if you can find a distribution, conditional distribution, given this trajectory, and then you find the maximum of that conditional distribution, you got the floor plan, or at least that's an estimate of the floor plan. Great. So you want to find the x at which this conditional distribution is maximum. That gives you the best estimate of the floor plan. That may not be the correct floor plan. It's the best estimate. Good. So let's try to do this. If you want to do this, what do you think you should do? I want to find the x at which that distribution gets maximized. What should you do? Argmax. So if you want to do argmax, what should you differentiate? You should differentiate this with respect to what? X. Okay, very good. I differentiate this with respect to x. But let me first write this as py given x times px divided by py. Base. Okay, guys. What distribution is this? Py given x. I give you x.
Gaussian.
It's a Gaussian at mean x. Because this is mean zero noise. And has a variance which is identity. Agree?
That means yes. Yeah.
Sorry, means CX. Okay. So this is a Gaussian. What is PX? PX is the prior, right, on what this X is like. Which means, remember, X was a floor plan, right? We want to estimate floor plans given the trajectories. So you say, hey, in general, what is the probability that you see on different kinds of floor plans? So one thing you might say, if a house has curved walls, that probability is very low, right? So this is that probability. Regardless of any trajectory, you can say what looks like a floor plan and what doesn't look like a floor plan, right? And what is PY? PY is the probability of these trajectories. Good. So now you want to do argmax on this. So you differentiate that. Okay? And this is a Gaussian, as we said. And because we do it in log, all of them become additions. Very good. Differentiating this Gaussian is very easy. What is the differential of e to the power x? E to the power x, right? So differentiating this is very easy. You get some constant terms outside, no problem. So this is grad x log px given y, differential of this. But look, you also need to differentiate this, which is grad x log px. And what is the differential of this with respect to x? See. Hey, but this is the problem. Grad x log px is this. This is what Hinton was asking me if I had this, but I don't have this. So I cannot solve this problem.
Is this related to Langevin?
But only if you have this, but you don't have this.
So this is his result. Right. That's the point of Langevin.
No, but Langevin only did x plus n, did not do cx plus n. Okay? This c made a difference. So this is why we cannot do Langevin on any random operation on x plus noise. We only can do x plus n. We'll see how, right? So you see, right, I'm now going to make an easier inverse problem where y is no longer cx plus n, but just x plus n. And now let's see what happens. Something very nice with it. Good. Okay, Langevin showed us a way to sample from fx if we can estimate grad log fx. Say we can somehow estimate grad log py, which is the gradient of log py. Then we can use Langevin to sample modes of the py distribution. We can call those samples generative data if we make noise negligible. I'll let you stare at that, because this is what this is what Langevin is saying. I'm just repeating. Okay. We are going to try to estimate this. Cool. Let's start. Y equals x plus n. Py can be written as pyx over all x, which can be written as py given x px. Please tell me if this is clear. True. What is this called? Marginalization. That's one thing that would surely remain in your dreams today. What is py given x? Gaussian. So you write this as Gaussian. You see, this is a Gaussian. Y minus x divided by 2 sigma squared times px. This comes here. Okay. Now I want you to put on your communication wireless Mobicom hat. Guys, what is this?
Filter data.
Convolution. This is convolution. Channel, signal. This is what you receive. Agree? Hey, what is this? Minus x, x, y, you integrate over x. Minus I, you integrate over I. This is convolution. What are you convolving with what? You're taking px, which is hi, and you're convolving with a Gaussian distribution on px. So you have px, which is your data distribution, and you take a Gaussian and you're blurring it. You're convolving the Gaussian with px. It is exactly this, right? Instead of this happening in 1D, this is happening in 4000D. Right? Every image is getting blurred because of that Gaussian kernel. Cool? So if you go back to our original picture where there were images in the desert, we are basically taking these images and we are blurring it to create this gray region, which is all the blurred image, because we've convolved this px with this Gaussian. If this Gaussian's variance is large, what can you say about the gray region? It will become large, it will expand. If this variance is very small, this gray region will be a small band around the image, around the images.
But I could have said that from the first line, right? You just added more text.
You could have said that from the first line, absolutely. Right? True. Yes. Okay. Now, let's do this. This is this. But look, this one and this one together, this is py given x. This one and this one. Oh, sorry. My bad. This is py. And now you take the derivative of py with respect to y. Okay. So because py has a y given x term and a px term, you differentiate by parts. When you differentiate px by y, what is it going to be? 0. So you don't care about that term. So you only care about this term, derivative of this term, by parts. So derivative of a Gaussian will remain e to the power x, e to the power Gaussian, but this part will come down here. Right? The exponent part will come down. E to the power fx is e to the power fx times f dash x, right? So this part's derivative is 2y minus x. That comes down over here. Good. But now look, in this derivative, this and this together forms the exact same Gaussian here. This and this together forms this Gaussian, which is py given x. Take a look at it and make sure it's clear. Only the x minus y, which is the derivative of that exponent, that came out. Very good. And the px remains because you're differentiating by parts. Here is the trick now. This is grad y log y, grad y py. Now divide this left-hand side by py. Okay. Look, grad y log py is 1 by py grad py. Right? Grad y log py. Remember, Hinton was asking for this. Right? Grad y log pi is 1 by py grad py. We have grad py over here, which is this, and we divide by py, which is here. So when you divide this, see what happens. X minus y comes from here. this py given x times px is here, and you divide this by py. True? This py just comes and sits here at the bottom of this. Now apply base here. Px given y. Sorry? Do I apply base here?
Yeah. That is the base.
Yeah.
Py given x.
Py given x becomes px given y. Oh, sorry.
It's just right
Px given y times py divided by px. That's this term times px divided by py. This is this. This px is here, this py is here. Base. Okay. What can I cancel? Good. So what you have is x minus y px given y dx. Agree? Separate it out. X times px given y minus y times px given y. True? What is this, guys? What is this integral? Why? This is one conditional distribution, but conditional or not, if you integrate it over x, it should give you 1. This is a distribution. So this is 1. So this must be y. What is this? Integral x px given y dx. Expectation of x given y. Right? Expectation of x is x times px integral. Expectation of x given y is x times px given y integral. Ooh. This is a minimum mean square estimator. I have given you y. I've given you a noisified picture. Right? We said x is a picture and y is some noisified version of the picture because I added noise to the picture. True? So I give you a noisified picture and I say, hey, which picture do you think this noisified picture came from? Agree? So think of it this way. This is a vector in 4,000 dimensional space, which is y. Right? And I'm saying, from which x did I come to this picture? And that is kind of x. Right? That's what I'm saying, right? And I'm saying now, whatever that x is, subtract y. So you basically subtract this y vector from this x vector. What do you get? This vector, right? This vector, right? Which is the noise vector. So this is basically saying whatever noise you added, the score function is that. Just that divided by sigma squared. Okay? So the score is basically, it's a denoiser. Right?
So if you give me y, I know the gradient is on, I just add it to y and say integral.
Correct.
And you can also connect this to previous lengths from this equation already. I get a noisy image, right? And then I need to estimate x from this noisy image.
Right? This was like, I'm in DC, I need to go back one step. It's exactly this, right? I'm in DC, tell me where you came from. Right? And wherever you came from New York, from whatever, right? From Virginia, from North Carolina, you take the expectation of that and you subtract y, you subtract DC. So New York is a vector, DC is a vector. You subtract DC from New York, you get the noise vector. So it's a denoiser.
One of the phases.
Correct. Okay, let me give you the full thing. This is related to some noise. If I increase noise a lot, this will be some estimate. So I can do this estimate for every different variance of noise. Does that ring a bell? For the large noise, I was trying to estimate x0. For the second large noise, I was trying to estimate x0. Similarly, if I make this noise go small noise, more noise, more noise, more noise, and so on, at every point I may try to estimate back the x. Great. I have my score function, which is a denoiser. So Langevin, Ito, Euler, all of these guys said, if you have this, they didn't know diffusion models, but they said, if you have this, I can give you samples from Py. And I have this because I have a minimum mean square estimator of x. And when I subtract y, I have a noise estimator. Very good. And Langevin, Ito, Euler, they said this is the equation if you want to get samples from a distribution pi x. I mean, okay, distribution log of yx. Remember, this is basically doing gradient descent on log of pi x. And this is a noise term, which is saying once you climb to the top of the mountain, don't just take that sample. Why not?
Some sample.
You want samples, right? You don't want the peaks of the mountains. You want samples around the peaks. Right? This noise term will give you that. So as you climb this log pi x, okay, this is clear, right? You're climbing log pi x. This is basic gradient descent. You're climbing log pi x, but when you go to the top, this noise term says move around. Don't sit at the peak of the mountain, move around. And then get a sample. So you're getting samples from log pi x. But we said log pi x samples are the same as samples from pi x. Right? And pi x, which is py, is same as px if the noise is small. Good. So you make that grad log pi y. This gray region is your log pi y. You do gradient descent on that. So start from a random point and do Langevin ascent. You have samples from log pi y. Right? You're doing ascent on the log pi y terrain. But recall pi y was a blurring with a Gaussian kernel. Why? Why is py was a blurring with Gaussian kernel? Because of this equation, right? Py was taking px and blurring with a Gaussian kernel. Because I did that, this gray region is my original x points blurred with Gaussian kernel, right? But I have a handle on log pi y. So, okay, so now the only problem that remains is, based on the noise that you've added, the gray regions grows bigger or smaller. Do you agree? If I convolve with a narrow variance Gaussian, this gray region will be what? Will be a tiny narrow band around these green points. If I do it with a large variance Gaussian, this will be larger, right? I want to do gradient descent on this gray landscape, right? So, but for gradient descent, I might start from here and I want to climb the gray, the distribution. But if I start here, I don't know what log py is. Why? Why don't I not know? Py is a noisified version of x. If I noisify with a small variance, then I know what log py is over here. I don't know what log pi is over here. So I have to noisify with a very large variance to know log py far away.
So how does this whole algorithm look like that?
Almost there. Yeah. Okay. So here is the full algorithm.
Just to connect a couple of things from you. So in the VE, we talked about how you add the noise in the latent space to kind of like join things together, right? Is that also the same kind of thought process
No.
here?
No, no. This is saying that you are taking the noise space, sorry, you're taking the images and you're noisifying it.
Yeah.
Why? Because the noisified distribution allows you to get grad log py. Why do you care about grad log py? Because if I get grad log py, I can do gradient descent on that distribution and I can get samples from py. Why do I care about samples from py? Oh, y is close to n, sample from py is close to sample of px. Sorry, y is close to x, sample of, right?
But I guess we, like, when you added noise in this latent space, you brought like the phase one of the moon and phase two of, like, you created that sort of bridge between it. So that's what I was trying to.
No,
if
that you
sort
should,
of-
that I think you should not think of it as a noise. You should think of it as a distribution. In VAE, you are learning a distribution so that all points from the distribution construct the same result. Okay. Here, you're doing it completely from a mathematical lens, because somehow mathematicians have figured out that noisifying the images gives you grad log py.
Okay.
And grad log py is all I need to sample from py, and that gives me samples. So it's a very bottom-up kind of a, because the math exists, I found a way to apply that math. This math exists from 1947. Right? Langevin was Pierre Curie's advisee. And when Pierre Curie died, Langevin and Marie Curie had a long-lasting, happy relationship. Okay? So that's where he comes from. He's a physicist. Good. So I'm done. The bottom line, what is going to happen is, I'm going to take this images, and first I'm going to noisify with a very large variance. Okay? What do you think about the gray region? It's going to completely cover the whole space. Agree? Good. Now I'm going to say, start from a random point and do gradient descent. Anywhere you start, there is gray region, right? Because you've noisified with a very large variance. So you do a bunch of gradient descent steps. And then I say, stop. Listen. So stop. And then I say, I'm going to now noisify this image with a slightly less variance. So that will be not the whole space, but it will cover a large region. And now I'm going to do gradient descent on that noisified space. So when I start doing gradient descent, that log py that I get is from a very large variance. But as I get closer to the peak, the log py that I have comes from a smaller and smaller Gaussian, smaller and smaller noise. If I did not do that, if I noisified it with a very large variance and then just did gradient descent, what is bad about that? That denoiser is very bad because you asked it to compute E of x given y with a very large noise. That denoiser is not good. But why do you need very large noise? Because if you start at some random point, you need some direction to do gradient descent. So you let it start from random point, do some gradient descent, but then stop it. And then say use a better noise. Then do a little bit more gradient descent. Better noise, do better gradient. So at the last step, you noisify x with a little bit of noise, and you say now do gradient descent. And wherever you reach, that's the image that you say, this is my generated image. In fact, this has very nice connections to simulated annealing. Right? Annealing actually wants to do nonlinear optimization. It perturbs the function with different amounts of noise, very nicely connected to simulated. Right.
How many? Don't do one step, do a few steps and then you change the.
Exactly, that's what you're doing.
How many steps?
Oh, capital T. You do capital T steps the way we did it in hierarchical VAE. That step should be very large.
But across all steps or
All steps. So imagine you're going to noisify it with 100 different Gaussians.
but for a single Gaussian, 1 step, 2 steps, 5 steps?
K steps, you can choose that. K steps, yeah. So if you have G different Gaussians, and in each step you are doing for each Gaussian you're doing K steps, your total is G times K, right? And G times K you say is 10,000, you can figure out how much G and K is.
So you said P to Y is like a noisy, like Gaussian with the noise.
Gaussian blurred of PX.
Of X, right? So the ascent that you're doing that's based on PY, it's already like you're not getting to the true place of where X. So my question is, why do you need the third term of additional noise?
This one?
Yeah, if you're already adding noise to the image and during your ascent itself, you're increasing that noise.
Okay. You have PX, which is what you want.
Yeah.
The peaks of PX is basically where this is 0, right? That's the peak of PX.
Yeah.
Let's look at what is the peak of this. Which means let's look at what is grad y in log of PY. When is this 0? This is 1 by PY.
Okay, so whenever that guy is 0, this guy is also 0. So okay. So the peaks are going.
Peaks are exactly the PX peaks and the Y peaks are the same.
You still need to add the third term.
You add the third term because you want samples. So even if you go to the peak of PY, you want to move or hover around a little bit so you get samples and not the maximum value sample. Right? You come to the peak. If you did not have this term, you're only going to get this sample. Right? But you want this sample, this sample, this sample, this sample. This noise term. Oh, I don't know how it is. This noise term.
Yeah, that one. No.
This noise term is going to allow you to get these samples. Hey, that's a knob, right? If I want my generative model to be more creative, what should I do? I should increase this noise. But be careful, it might just go far away, it might hallucinate and give you something bad.
But you can also go to your steps.
You can also, that might be a little bit risky because yeah, you may not go to you're saying I can just stop here. Yeah, maybe it's good, I don't know, I feel comfortable going to the peak and then hovering as opposed to without going to the peak, stopping early on. So this is connections to Langevin and I think we'll skip. Sure, please.
So you want to draw, you want to find what is the algorithm? What is the algorithm? Draw a random Gaussian sample, right? Or something like related to the previous one. And then I'm trying to get what? So
okay, let me tell you the algorithm step by step. I have n pictures. They're all in some 4,000 dimensional space. Okay, they're scattered in 4,000 dimensions. Okay, I take those n pictures in 4,000 dimensional space. I first take one big Gaussian dome, which has very large variance. I take that dome and I blur all the pictures. That will give me log of PY. Right? And that log of PY spans the whole space. True? Let's call that distribution log of PY the first distribution. Then I take a smaller Gaussian, slightly smaller. I go to the pictures again and I again blur it. That gives me another thing, I call that second distribution. So I have first distribution, second distribution, third distribution, so on. And all these are like getting closer and closer to the images, right? The first one is very flat, the second one is closer, third one is closer, and so on. I'm done with my blurring. Now I say, let's do gradient descent. I pick a random point. And I say, use the first distribution to do K steps. You do K, you rise up some K. Then you say, stop. The next K steps you do with the second distribution. You rise up K. You go so on. You end up with the last distribution. You go K steps. You're on top of something. You say, that's my first sample.
So this is really similar to start with the white noise in the diffusion, then you do the steps.
Exactly.
Yeah. So just to see, when you put a lot of noise, it's equivalent to X capital T. Right here, we choose a super large variance. And in the middle step, now you go one step. So here you are doing ascent. This is what? this is xt minus 1 given xt. This is xt minus 1. T minus 1 given xt.
Correct.
Right? You do a set. And then, of course, plus some noise. And then after some steps, let's say you come back to x200. You add a smaller noise, and then you still do a set. So this is, so here, this is x199 given x200. Until you do x0 given x1 here.
Does that make the connection? It's exactly the same.
And just to understand, these x's here that you start off with, if you have like 100 by 100 pixel image, it's, so in that case, the x is at 10,000.
Absolutely.
And basically, your xt is just a Gaussian sample of those, you just 10,000.
X capital D.
X capital D.
It is a random sample.
Yeah.
From the whole space.
So it's the same in the GAN where you started off.
From a Gaussian.
Gaussian.
This sounds analogous to how recursion iterations are basically some of the same.
Right, right.
It has that feel, that the two views are staying the same.
Similar thing, exactly.
It's just that one is sort of more recursive and it's not from zero to x1 to x.
Right, totally, totally.
And then this is
Exactly,
describing it fully.
exactly, exactly. And simulated anyway, they have very beautiful nonlinear optimization techniques, has a lot of similarities.
A question is how, I think you mentioned that, in the sort of initialization stage, you have to make sure all the images you have across the whole space, like 1000K dimension, sorry, 4K dimension space, like how do you make sure of that?
Oh, how do I, can someone answer that question? That's a good question.
Because the way.
So his question is, how do you make sure, if you start from a random point, how do you make sure you'll go to all the different kinds of pictures that there are in the data set?
You could have a bar parts, but again, suppose, for example, we have a 1 million image. What if this image, if you embed it into 4,000 dimension embedding space, it just scatter a point corner. And you have a whole outer space just leave blank.
Correct.
There's no data point there.
Correct.
And the way you describing how this generative model works is simply you decrease the variance step by step, and eventually you will have you will sample around a peak.
Absolutely.
There's a peak.
Absolutely.
Will center at the sample you already know.
Absolutely.
Yeah. Then how do you generate the sample from the data you don't have?
You don't. If you have not shown the model a blue butterfly, it will not generate a blue butterfly. The question is, you can ask, is that a good thing or a bad thing? Someone will say it's a good thing because blue butterflies don't exist in reality. Someone will say that's a bad thing. As an artist, I should paint blue butterflies. Who's stopping me? That's creativity.
I think that we can ask it. Or if you think the image case, you could have a lot of cameras around and can capture a lot of images.
Mhm.
The space can be well scattered, but the variable or wireless single space. We really, maybe we don't have that capability or low field data sets. In that case, maybe the data point we observe cannot span all the space.
But why do you want to go to a different data point? If all your wireless signals have some property in it, let's say their autocorrelation is 0. Let's say they're very much pseudo noise kind of signals. Let's say, why do you want to generate a new signal?
Maybe that's because of the device we have like power constraints, we cannot observe that signal.
You have to have the data from that.
Yeah, from the form of the
Yeah.
general.
This one will only go to the modes. Do you know what modes are right now, right? In a probability distribution, wherever there are these mountain ranges, right? These hills, those are called modes. This will go to the top of the modes. And the modes will very much be determined by where there are images. Right? There is no false mode because there's no image there. But creativity means you should go up some mode in which you've never seen data. Okay. I want to ask you a question. If you start from some random point, can you go this way or this way? Or will you always go in some direction? Why will you ever go in that direction? So I take these images and these images and I blur them. From here, what does this gradient compute as? Or what will that gradient be? My question is bad, so I'll give you the answer. This gradient is going to be influenced by this guy's pull and this guy's pull. So your gradient is going to be some weighted average of those two's pull, right? So you're going to tend to go towards the one in some average direction. But if it goes in some average direction till here, this guy will then pull it harder. If it goes in some average direction here, this guy will pull it harder. And that's where that noise term will be very helpful. If that noise term wasn't there, you're going to keep going to the same mountaintop from that starting position.
Again, every step.
Every step. Exactly. That gives you generativeness as well.
With some really basic questions. So in your training data, if every image appears exactly once, right, it's unique. Then what's the distribution of those images? It's just uniform. You know, they're equally likely
They're equally likely
to be produced in the final.
Correct. But one way to create the distribution is put a delta function on all of them. And maybe give the magnitude of the delta function as 1 by n, which is n number.
Each peak is equally likely.
Each peak is equally likely. But what you want to do is, if there are images that are nearby, your maximum likelihood say, instead of putting delta functions everywhere, put something here because there is some smoothness in the images.
Maybe one more question.
Sure.
There's a nice intuitive match from what you said now in the diffusion. At these steps, I started to run on each step is running the sun. Yet there was a neural network there which I was training one way, and here I do something different.
Where is the neural network here, guys? This is going to be theta.
This is exactly the same.
This is a denoiser.
It's the same way I calculated. So if I do the calculation, I'll get the R.
These two will be exactly equivalent. Remember, your y equals x plus n, right? So your noise distribution has to match what you did in the encoding process there. So the tutorial, the diffusion tutorial, which is really a very well recommended tutorial, they say there are 3 views of diffusion. They all lead to the same place. 1, given a state t, you estimate, you train for the mu, the mean of that Gaussian distribution that decodes. That's 1. Right? At every point, you estimate, you predict the mean of the previous step of that distribution. 2, at every point you predict x0. Because from x0 you can again go back to t minus 1. 3, you predict this MMSE estimation, you predict this denoiser, this score. That gives you exactly the same thing. Now, empirically, people have seen this works better. No, I don't know why. Math is the same, empirically this works. To me, this is more clear.
What does better mean? They're getting nicer.
That's a very good question, actually. What does better mean in generative models? Suppose I give you 2 generative models. How will you say which one is better?
All close.
Huh?
All close. Less noise and more close to.
How would you say less noise? It generates a picture. This other generative model generates a picture. You don't know what the original picture is, so you don't know how much noise there is.
Easier to train.
Huh?
Easier to train, faster to converge.
No, in terms of quality of images, how will you say which is better? Here is the beautiful thing, or the sad thing. There is no way to say what the image generation quality is. It is very subjective.
Actually, I have a problem. Maybe you dominate.
Right.
The bigger discussion.
Correct.
So I think the problem population itself changed actually.
Okay, very good, very good.
Let's stop it.
But I just want to say, the way that people do today is they've designed new metrics, which is the following. They said if the generative model gives me one image, I cannot say much about the generative model. I'll ask the generative model to generate 1,000 images or maybe 1 million images. Now what will I do? I'll take those 1 million from generative model 1, I'll take the other million from generative model 2, and I'll match distributions of the real images with this first million, of the real images with the second million. And I'll see which one matches in distribution. How can I do that? Remember, these 1 million images are points in space, right? In 4,000 dimensional space. So I can match distribution, I can compute KL. For the second one, I'll compute KL. Whichever matches better, I'll say that's the better KL. That's...
Question I have. You don't have the distribution, there are samples of it all.
Yeah, but if you have samples from distribution, you can do matches. That's what KL divergence will say. KL divergence will say you take samples from one distribution, and for that, you basically take the ratio of samples from the other distribution and this distribution. KL's equation says
You have a PM, so the X is the image,
right.
So the two sets of images I'm producing, I may not have the
Right.
same.
Yeah, I don't remember what that metric does. I think it approximates this PX.
I think it will make those distributions sort of smooth, right? With the least order polynomial in the curves.
Yeah, I don't remember how FI. There's this thing called FID, which is Fresnel. What distance? Some Fresnel something distance, and it computes the distribution. And I forget how exactly they do that. Yeah. Yeah, maybe there is some smoothing, and then they match it under that smoothing constraint. I think we can stop here. I don't know if there are any more questions, but there was, I just want to show you, there was GAN. You're getting it, right? You're getting everything you're doing here? Good? Everything good? Yes, yes. Oh, this is great. You understand perfectly.
Why don't you create the record video? So that's the-
Sure. No, that's not the end. I want to show you. Okay, you got all of that? Here's one more. Okay, all of this is on the slides that you have. Done.